And let me continue lectures devoted to modeling of linear polymers. So this is my screen. Let me rotate my tablet. Last time we discussed that the simplest natural model for linear polymer can be trajectory of some stochastic process. The most popular model is based either on the simple random walk in different dimensions or with continuous time on the Wiener process. Yesterday we have seen that due to the mathematical properties of the Wiener process, we face a new problem related to existence of the points of self-intersection, which are absent in the real life for linear polymers. So, in order to overcome such difficulty, we first of all have to understand completely how to calculate this point of self-intersection. It was began at the yesterday lecture. Now we will continue this, but let us do it in more general case because we already have checked that maybe this independence of increments and moreover some kind of difference between the beginning and the end of the polymer line is non-natural. So it is interesting to ask for some case of some class of processes which can serve as a model for linear polymers and have no such very good but slightly unnatural properties as Wiener process has. As I said, the reason why we have to look on something else is the absence of direction in real molecular for linear polymer, and by the way, non-smoothness of trajectories of Brownian motion. The second property we will discuss slightly later. Now consider one class of Gaussian processes which have not Markov property but very similar to the Wiener process. Such a class of processes was proposed by me in 1988 for purposes of stochastic analysis. But it occurs that it can be used here. The definition of such process looks like a centered Gaussian process xt is called by integrator if there exists some c which is greater than 0, that for all partitions of the interval 0, 1, and all sets of real numbers a0, so n minus 1, we have the following inequality. The expectation of the sum k equal 1 to n minus 1 ak x tk xtk minus xtk tk square is less or equal than c sum from k equal 0 to n minus 1 ak square delta tk. Of course, in this sum, everybody recognize the following. If we consider step function, which take value ak on the interval tk plus 1, then at the left-hand side, we have a second moment of the integral, which from this step function with respect to the process x. We don't need any properties of the process in order to integrate step functions against it. So we can consider such integral, and it occurs that it can be estimated uniformly by the integral of the square of this step function against 0, 1. So this allows us to expand procedure of integration on any with respect to x on any function from L2, 0, 1. This explains the name of the process. They are called integrator. Let me recall you that Wiener process has the same property. Even for Wiener process, for Wiener process, we have equality instead of inequality. So integrator is a class of Gaussian process with good properties from the point of view of stochastic analysis. For us, it is important the following fact. It can be proved that every integrator can be associated with the linear continuous operator R, A, in L201 via representation. Here you see the following representation. What is written here? This is an action of operator A on the indicator function of the interval 0t. This capital unit indexed by 0t is an indicator function of the interval 0t. It's equal 1 on the 0t and 0 outside. We apply operator A to this function and then get the function from L201 integrated against Wiener process. So one can imagine that properties of xt are completely defined by the properties of the operator A. So with some, let me continue with some, W is a Wiener process. Wiener process. Then one can imagine that A determine properties of X. And it occurs to be true. We will consider very special case, namely when A is a identity operator plus K. Here K is a compact operator. K is compact operator. Operator in L201. Let me recall you the main property of compact operator, which can be considered as a definition. If so, this is just recalling what is compact. If we have sequence Hn in L201 such that for all J we have the scalar product in L201 Hnj converge to 0 when n tends to infinity. Then then A Hn tends to 0 and n tends to infinity in L2, 0, 1. Excuse me, not A, but K. Mhm. This is just recalling what is the compact operator. It turns every weakly convergent to 0 sequence into strongly convergent to 0 sequence. From the first point of view, it looks like very artificial. Why we need this compact perturbation? We just discussed very concrete problems related to self-intersections of the Wiener process or some process which will model for us the linear polymer. Why we discussing some boring stuff from Hilbert space? The reason is the following. You remember that a main property of the Wiener process is independency of increments. W has independent increments. So one can consider, one can formulate this very useful property as follows: that we can consider, for example, a 2-point T1 is less than T2, and for sufficiently small delta, which is sufficiently small, consider two the increments W T1 plus delta minus W T1 and W T2 plus delta minus W T2. Of course, when delta is sufficiently small, these two increments are independent. But I can represent these increments as follows. It's equal to integral from 0 to 1, indicator of T1, T1 plus delta, S dws, and the same here, also integral from indicator. And the property of these two increments to be independent can be now formulated very geometrically. We just have that the scalar product of these two T1 plus delta and indicator of T2 plus delta is equal to 0. So we understand that the property of Wiener process to have independent increments is related to the orthogonality of some indicator functions in Hilbert space. Now, let us note that our integrator with compact operator K satisfies the same property asymptotically. Namely, it happens that if I consider again A equal identity plus compact operator, then I have that that the following relation holds. A from indicator T1, T1 plus delta. So we apply A to this indicator, then divided by square root of delta. So what I did, I just normed this indicator to be unit vector in L201. Then multiply on A here. Or even we don't need it. Here, excuse me. Multiply on indicator T1, T2, T2 plus delta square root of delta tends to 0 when delta tends to 0. So from this point of view, one can consider the integrator x related to this operator A as follows. We have the trajectory of the Wiener process. For example, this is the trajectory of Wiener process, and we make some relationship between different parts of trajectory. Yeah? We just relate these different parts. I mean different parts along the time of motion along the trajectory. We relate via operator K. Via operator. So this compact perturbation is a natural generalization of the Wiener process, because asymptotically, when we have very small increments, the behavior remains the same. But on the large intervals of time, we have something else. So it occurs that really such integrator X, which is called compactly perturbed Wiener process has asymptotically on the small interval the same properties as Wiener process. It can be proved, for example, that X satisfies the law of iterated logarithm, has Levy model continuity like square root of logarithm t, exactly as Wiener process has. Also, it can be proved that it has a point of self-intersections on the plane. By the way, we cannot say now that it has properties point of multiple self-intersection for general compact operator K, but if K is Hilbert-Schmidt, this is a more restrictive class of compact operators, one can check that our integrator X again has with probability 1 point of self-intersection of any multiplicity, even count of multiplicity. Now let us consider the the procedure of counting of self-intersection. Let me describe for you procedure which was derived by Evgeny Borisovich Dynkin. Then we will do the same for integrator. So Evgeny Borisovich Dynkin propose to consider the following construction. Dynkin renormalization. Denote by delta k the set of points S1, Sk, such that 0 is less than S1, less than S2, less than Sk, less than 1. This a simplex of dimension k. Then trying to calculate the points of self-intersection of multiplicity k, one can write the formal expression. This is integral for delta k. Here is the product from j equal 1 to k minus 1, delta 0, w tj plus 1 minus w tj. Yesterday we discussed that this expression is only formal and must be defined properly. And one of the natural ways to do this is to consider approximation to delta function. So let us use p epsilon, which is density of Gaussian distribution in the on the plane with 0 mean and epsilon identity covariance. Then why we choose p epsilon? For arbitrary function phi, which is continuous and bounded on the R2, we have the following property. The integral from R2, which is here is p epsilon u pi epsilon u du, tends to phi 0 when epsilon tends to 0. So let us substitute into tk the function pi p epsilon instead delta 0. We get the expression p k epsilon of the kind integral from delta k with respect to delta k. Here is the same product j equal 1 to k minus 1 p epsilon w t j plus 1 minus w t j. This is a well-defined random variable, and one can try to look at its limit when epsilon tends to 0. Yesterday we already said that this limit does not exist, and we need to subtract something. It occurs that one can define the following expression. Tau k epsilon, which is equal to the sum from L equal 1 to k. Here is 1 over 2 pi logarithm epsilon in power k minus L. And here is c from k minus 1, L minus 1. This is binomial coefficient. And here is T L epsilon. What is written here? Actually, it is constructed very simply. Yesterday, we have seen that the expression where we have the delta function from a difference of W, from increment of W, blows up when these two time arguments became to be close. So it was caused by the scaling property of the Wiener process. So we have a lot of self-intersection near the same values of the time argument. To avoid this property, we just subtract diagonals from the simplex. And you see here exactly the simplex of the smaller dimension. The number of such simplex is like this binomial coefficient. And here we have the multiplier logarithm epsilon. It is also very easy to understand why logarithm epsilon, because yesterday we have seen that expectation of the delta function of the increments of Wiener process looks like 1 over difference tj minus tj plus 1 minus tj. After integration, we have epsilon. It is a rough explanation, but it reflects pure reasons. And now, by thinking, it was proved that there exists a limit in any LP, and this limit is called renormalized when epsilon tends to 0 plus, and tau k is renormalized self-intersection local time. Self-intersection local time. Time for Wiener process. As we said, the compactly perturbed Wiener process must have the same properties, and it occurs to be true. And it was proved by me and my former PhD student Olga Izumtseva that for compactly perturbed Wiener process, the same renormalization take place. So we can again define renormalized self-intersection local time. Okay, so one can ask the following very deep question. What is the relationship? What is the relationship between self-intersection, renormalized self-intersection local times, and geometry of the process, of the trajectory process trajectories. This is a natural question because we yesterday discussed it. For example, that we trying to calculate some characteristics like radius of gyration. We trying to calculate some self-intersection in order to build some measure like Boltzmann did, which will give a very small probability to trajectories which have a lot of self-intersection and so on. So we have to understand this geometry well. And in this direction, one can produce the following statement. It was proved by Olga Ezulso and Mini that, for example, the following theorem holds. For example, for compactly perturbed Markovian process. The tau2 is, excuse me, not tau2, but expectation of tau2, and we know that norm of x1 is equal to a, is O small of a minus alpha when a tends to infinity for any alpha greater than 0. So we see that this, at least this, excuse me, square, at least this self-intersections decrease very rapidly when we have trajectories which have a long end-to-end distance. Let me recall you that we start from 0, so we have end-to-end distance exactly equal to a now, and it can be proved that such such formula holds. So the trajectories which with the long end-to-end distance have a small amount of self-intersection as we expect. Moreover, the much deeper result for Wiener process was obtained by Legol, and it characterized some geometry of the trajectory of Wiener process on the fixed time interval. Let me explain it to you. So it is related to area of Wiener sausage. It is just a mathematical joke. Of course, we have to be precise and say epsilon tube. What I mean, let me recall you the form. Suppose that we have the curve in the, for example, in the space, and what we do, we just take epsilon greater than 0 and organize a union of all balls which have a radius epsilon, and centers in on this line. Then we will get such tube, which has radius epsilon. We can do this on the, for example, on the plane. Then one can consider S epsilon is area of the tube. It occurs, and now it is trivial, yeah, that when epsilon tends to 0, S epsilon has asymptotic expansion like pi epsilon square. This is due to these two ends of our line, plus epsilon multiply on the tail of our line, yeah, at least. So in this space we have three terms: epsilon square, and epsilon in power 3, and the term epsilon related to epsilon square is connected to gyration of our curve, and so on. So one can think at least that the asymptotic expansion of the area of the small tube along the line reflects its geometrical properties. And it's true for smooth function. Now, what was proved by Legal I think it was near 85, because he published three papers with three different proofs, but more or less at the same time. That if we consider, instead of the smooth curve, consider the trajectory of the planar Brownian motion. Yes, this is Brownian motion. We again organize this tube, but I am not able to draw a nice picture. Just I try to give you imagination what happened. Then we can again consider S epsilon, and it occurs that it has asymptotic expansion, but roughly speaking, this is asymptotic series, like sum from k equal 1 to infinity. Here we have what we have: 1 over pi logarithm epsilon in power k. And here we have some coefficients. I think that it is like okay, this is coefficient came from geometry, which does not depend on our considerations. And here we have renormalized time of self-intersection. So you see that we have two non-trivial things, minus k. Two non-trivial things. First of all, the area decreases like 1 over logarithm 1 over epsilon, not as epsilon. Secondly, the coefficients are local time of self-intersection. So from this point of view, one can say that local time of self-intersection plays a role of geometric characteristic of trajectory of the Wiener. As I said, all these facts make the model of the linear polymer based on the Wiener process or on the compactly perturbed Wiener process, which is just more wide but similar class of Gaussian processes. Very well studied and useful for statistical applications. But as we have seen yesterday, we have several properties of the molecular of real linear polymers, which still not reflected in this model. The first one is that, as we said yesterday, some of molecules of linear polymer has a self-crossing property like DNA has. So they can change their topological type. Imagine the knot in the space, and this knot became to be alive. It can change its type. For example, if you have so excuse me, if we have such kind example of knots, then it can happen that one time it became to be unknotted, and then go further with other transformations. So this is a usual behavior of DNA in the liquid. By the way, we know that, for example, human DNA is not a closed curve, but there are some kind of some form of bacteria which has DNA exactly as a closed curve. And as we mentioned yesterday, this topological type, this shape of polymer molecule, DNA molecule, cause its topological property. So, cause not topological, cause gene expression properties of this molecule. From this point of view, it can be interesting to build such model which can evolve in the time and change topological type. Now I begin to present to you such model. In order to do this, we will start from slightly different notion, which is a Gaussian random field in the Euclid space. So let us start from the notion of a Gaussian random field. I will consider three-dimensional case, but of course, most of considerations can be done in arbitrary dimension. So let's start from the definition. We will call eta, excuse me, definition. Centered a Gaussian family eta u, where u belongs to R3, is called Gaussian random field with covariance function y capital if for all uv which belong to R3, the expectation of eta u eta v is equal to phi u v. I present this very simple definition in order to emphasize that as we all know, the properties of eta are completely defined by the covariance function phi. This covariance function cannot be arbitrary function. We know that it must be non-negatively defined, namely, we know that for arbitrary u1, un, which belong to R3, and lambda 1, lambda n, which belong to R, we must have phi u I u j lambda I lambda j now sum from ij equal 1 to n must be non-negative. It is trivial because this sum is nothing else than the expectation of the square of the linear combination. Now, for us, the main examples of such capital function phi will be a smooth function which depends on the difference u minus v. So a good example will be the following. Phi u v is just equal to the exponent minus 1/2 norm of u minus v squared. Of course, it is a good function, but what we need to understand that this is a really non-negative. Why we have here the property of to be non-negatively defined. Okay? And one can prove this by in different ways. We also would check it using the following representation. Suppose that we have this p1 square root. This is a density of normal distribution with one square root of, excuse me, no, without square. Excuse me, we don't need it. of the normal distribution with the covariance equal to 1. Then, what we know? We know that convolution is equal P1. Yeah, it is a trivial property of standard Gaussian distribution. Related, based on the fact that when we have the sum of independent random variables, the variance is added, and the density of the sum of independent random vectors is a convolution of the densities. But from this point of view, we know that this convolution is nothing else than integral of R3 P1 half U minus something, for example, minus R, P1 half V minus R, and here is dr. Yeah, and we know that it is equal to P1 U minus V. Yeah. So then I can say that if I multiply these densities on some constant, I will have the representation that our function phi u minus uv can be represented as the integral of 3 from some function h u minus r. Here is h v minus r. From this representation, it follows immediately that phi is a non-negatively defined function. So then we understand this and understand that the Gaussian random field with such covariance exists. Moreover, this is a very good random field in a sense that, first of all, it is rotationally invariant and shift invariant. Sometimes such random fields are called isotropic random fields. Their covariance just depends on the difference of the arguments. So now eta is isotropic random field. Eta is isotropic. A random field. It means that if I take matrix U which is unitary, it means that U adjoint is equal to U minus 1. And it is related to orthogonal transportation. Yeah. And I take arbitrary vector B from R3. Then a new field, eta tilde of U, which is just eta of U plus V. So we rotate our field and multiply and add some V is equal in the distribution, yeah, because it will have the same covariance function. Moreover, it occurs that that eta now in this example has smooth realizations. What I mean that one can find such modification of eta that eta omega belongs to C infinity on R3 almost, yeah. So eta is a good random field, and now let us construct the random curve using random field eta. What we will do? We will consider a new field. Let me define it like F capital from U, which is equal eta 1, eta 2, eta 3 from U, where eta 1, eta 2, eta 3 are independent copies of eta. Then consider gamma which is closed smooth curve in it. It can be some circle, for example. What we will consider now the image F from gamma is a model for linear polymer. So what will happen? We just have smooth curve in R3, and we have mapping F. Let me emphasize again that F is random. So here we have some knot. Let me try to write something. And what we know? At least we know that it is a smooth curve. We don't know at that moment nothing about knotting, but one can imagine F is random. Why not? So we will study the properties of this knot in the next lecture at Friday. For today, that's all. Thank you for your attention. Maybe somebody have questions or comments, please. Okay. If there are no questions, thank you again, and bye up to Friday.
Goodbye. And now we will have a break, and in 15 minutes we continue with this next lecture. So please don't go very far. Okay. Thank you.